All right. Some other laws related to gases involve Dalton's law of partial pressures. All right, so this relates to how mixtures of gases and the pressures of the individual gases relate to each other. All right, so you'll know you've got this when you can correctly describe and calculate partial pressures of a mixture of gases. So John Dalton studied mixtures of gases, and he observed that gas mixtures, like air, is a really good example of a mixture of gases, have multiple gases within them. All right, so you've got oxygen and nitrogen and carbon dioxide and all these different gases in air. Yet air itself acts just like if all it was pure nitrogen. All right, it has the same gas laws, Boyle, Charles, things like that all apply to air, just like it would to just pure oxygen and pure nitrogen. So he also noted that the individual gases are able to behave independently of the other gases in the mixture. All right, so even though air is carbon dioxide and oxygen and nitrogen, yes, they can act together as one entity. You can also treat the oxygen on its own. All right, so he found that the individual gases contribute a component to the total pressure of the system. So his law is this. All right, your total pressure is going to be the sum of all of the individual pressures. All right, I've got this ... here because it depends on how many gases are in your mixture. All right, if you have 10 gases, then the total pressure is going to be the sum of the individual pressures of those 10 gases. If you only have 2 gases, then the total pressure is the sum of the individual pressures of the 2 gases. So let's see what this looks like. All right, you have oxygen and nitrogen in a tank. If the pressure of the nitrogen is 1.61 times 10 to the 4th kPa, the pressure of the oxygen is 4.34 times 10 to the 3rd kPa, what is the total pressure? All right, so in this example, we have 2 gases. So really, we don't need the rest of the equation here. Pressure 1 plus pressure 2 is going to be equal to our total pressure. All right, now, those of you that are unfamiliar with scientific notation, big quick review here. This 1.61 times 10 to the 4th, what that means is that this decimal was shifted 4 times to the left. So really this number is 16100. All right, so to get it back to that 1.61, you do 1, 2, 3, 4. Okay, so that's what's going on there. Now, the 4.34 times 10 to the 3rd, that is going to be 1234340. Now I can easily add these two numbers together. All right, 16100044402, and say you gotta put this back into scientific notation to get your final answer. 2, 3, 4. It's gonna be 2.044 times 10 to the, how many times did I move that? 1, 2, 3, 4. So there's your total pressure. Okay, remember we just added those. So here's one that doesn't have scientific notation, so it should be a little easier on you mentally. But you have a mixture of argon, helium, and oxygen. Has a total pressure of 1,015 kPa and a partial pressure of argon and helium of 152 kPa and 305 kPa respectively. So what that means is that your argon pressure is the 152, your helium pressure is the 305. What is the partial pressure of oxygen? All right, so remember, so let's see, this time we've got 3 gases, so we've got our P total is equal to P1 plus P2 plus P3. All right, so you know two of the pressures, you've got to solve for the third one. What do you get? So my total is 1,015, then 152 plus 305 plus my third pressure. So this is just going to be my P3 is equal to 1015 minus 152 minus 305, which gives you my partial pressure of oxygen is going to be 558 kPa. Okay? So another sort of example that you can have these partial pressures, because you're just adding things to get totals, percentages play in really well. So at a depth of 40 meters, the water pressure is 600 kPa. A diver breathing air, 78% nitrogen, 21% oxygen, would have what partial pressure of nitrogen in his or her lungs? So, one thing, just in case you don't know it, for our bodies to work, the pressure in our lungs has to be equal to the pressure around us. Otherwise, our lungs would collapse if we didn't equalize our pressures. So the pressure of the air that's in our lungs, the nitrogen and the oxygen, has to be equal to this 600 kPa. All right, so if we know 21% of the gas is oxygen, that means 21% of our total pressure is going to be related to the oxygen. All right, so what you do is you take that 600 and you multiply it by 21%, which is 0.21. And you get 126 kPa is due to the oxygen. And we were supposed to answer for nitrogen. So, same idea. You're just going to take that 600 and you're going to multiply it by 0.78 because it's 78%. So that's going to be your O2 and that's going to be your N2. All right. All right, we're going to forget this part. Because as I read through this more, this is way easier than I initially thought it was. Well, I have an example of combining ideal gas law with these partial pressures on another slide. But this one is, don't let all of this extra information throw you off. So you have, at 298 K, you're going to collect 0.5 liters of oxygen over water that has a total pressure of 175 kPa. What is the partial pressure of oxygen? So if you have a total pressure of 175 kPa and you're told that the partial pressure of your water vapor is 3.6 kPa, all right, so you've got your P total equals P1 plus P2. What do you think you do? You got your 175 equals the oxygen plus 3.6 kPa. So your O2 is going to be 175 minus 3.6, just 171.4 kPa. So we'll do this one together because this is what I was thinking of before. So, due to Dalton's law of partial pressures, all right, we can use that in combination with our ideal gas law. So if you remember, ideal gas law is PV equals nRT. All right. In order to figure out the partial pressure of fluorine, since we know the moles of fluorine, all we have to do is plug that in with these other values, our temperature, our volume, and then R is going to be the 8.31 value because that is the liter kPa mole Kelvin version, and all of our choices here are in kPa. All right. So I'm going to have P times 5.0 equals 2 times 8.31 times 273. So 2 times 8.31 times 273. So I have P times 5.0 equals 4,537.26. Divide both sides by 5. And you get 907 kPa. So as we learn these new concepts, don't forget the laws we've already learned about. They will come in handy again for different applications. All right? So definitely have all of those equations and things like that in your notes somewhere. That way you can apply them to these new ideas that we continue to talk about.